Alright, Kevin Van de Kar here. Welcome back to Unit 3, Module 3. So today we're going to talk a little bit more about transformation. We're going to go into the scene and nodes and the scene graph in more detail. So yesterday we kind of scratched the surface on all of those topics, and today we're really going to drive it home. Before I get started, I'd like to go over the exercise from yesterday. So basically, it was to create another utility object, so that should have been very straightforward. And then once you were, you have the skeleton built, then we asked to use the resource tools to add a button, add a function to create a box, and this is the gen box object, and then add the box to the scene, and then apply a basic transformation so that it's at a location other than the origin. So let's take a quick look at that. First of all, if you go into the resource editor within Visual Studio and you use the resource tools here, so basically the RC file opens up and you have the resource editor. Now you could hand edit the RC file as well, but it's easier to use the tools, I think. And you just had to create a button, so you'd select the button and basically draw the button on there, and that's going to give you an ID. So in this case, this new one is IDC button 3. Okay, so that button is then associated with the source code excuse me, over here. So there's a pre-made dialog process, and in my case I just named the lab exercise 2. And in the command section, there was a pragma saying to do, and this is where you basically can receive the callbacks from the user interface controls. So it's going to, whatever you do is going to initial a WM command, and then within this block you can switch based on the low word, and that's going to give you the specific resource of the control that initiated it. So IDC button 1, I created a function that's on my class. It's a static function that, it's just going off the static instance called create object scene, create scene object. Okay, so if we take a look at that function, here you can see my interface pointer is getting the core interface. Now this is defined in the class as a private member. Okay, so you can see there it's an interface. The creation is done through the create instance, and you had to find the class IDs. So this is the superclass ID, geom object class ID, and then the more specific one for the box object is box obj class ID. And remember, you had to use the macro with the A and B components, and because this is one of the older objects, the B component is just always 0. So while we're here, let's just take a quick look at the definition of where these live. So they are in plug API, and we mentioned that yesterday. And whenever you need to create some of the built-in objects, this is kind of handy just to have open so that you can see the definitions for them really quick. Some of them are abbreviated in certain ways, like geosphere and the box object, etc. Okay, this is also where the superclass IDs are. So if I scroll up here, these are controllers, and here's the different superclass IDs. So for example, there's geom object class, right? And these are all reserved; they can never be duplicated. So the idea is that these are always your superclass IDs, right? Depending on what you're deriving from. This plug API also has a lot of other information in it, and one other bit that might be important is the API release numbers. So you can see here that there's definitions for all the different public releases of 3ds Max, going all the way back to version 4 on DOS in 1997. So if you have a code base that old, you can use the pound defines to determine whether your code will run. So not advised to keep code around that long, I don't think, but surely Max has been around that long. Alright, so we jump back over here to the code, and we use the gen box that we created, and we set the parameters. We create object node off of the interface pointer, and we basically assign this object that we created, the gen box, to that node. So now the node exists and the box exists, and they're part of the scene. And then we just simply change some parameters on the node, like we're going to set its name, you're going to set its wire color, and then we set the node's transformation matrix, and then we provide an offset. And this wasn't required, but it was just something that I showed yesterday. Alright? So let me know if you have any questions on that. Okay, and the last portion of the exercise was this extra section, and it was basically to add another button to create a cylinder with the bend modifier attached. So we switch back over to the code. It's very similar to what we did before, but I think it's worth looking at. First of all, the cylinder object itself is slightly different than the gen box object. So first of all, in this case, we do a create instance, and we're just casting it to the more generic object type. So this doesn't matter too much. So now we have a P object, and off of P object, we're going to get the parameter block, and in this case, it returns an older style of parameter block called the iParam array. Okay, so we've got a pointer to that array now, and in order to find the index of a parameter in the array, we have to go back to the object, and we call getParamBlockIndex with some definition. So in this case, it just happens to be 0, and that's going to give us the radius index in the array. So it's a little bit clunky how this works, but it does work. So in order to set the radius, we first have to ensure we have the right index into the array, and then we go to the array and we say set value on the index of the radius to the value that we want. So the radius is going to be 30 in this case. Okay, so we do the same thing for the height and the number of segments, and that gives us the basic geometry for the cylinder. Now, in order to put a modifier on it, we have to do this this operation called create derived object. And what that does is give you back an interface to that new derived object. A derived object we'll talk about later, but this is the base place where a modifier would be attached. Okay, so we've got the derived object created, and the next thing we're going to do is create a modifier. Okay, so in this case we just do the create instance again. In this case the class ID is here, and now we've got a bend modifier constructed in memory. To set up the values, you can see that this is actually using the more current parameter block. So iParam block 2 is the latest version of parameter blocks. So here we go off the bend modifier that we've constructed, and we get the parameter block at index 0. So in this case there can be multiple parameter blocks as well, but in this case there's only one, so we're going to just get 0. Okay, so now we have a pointer, an interface pointer to that parameter block 2, and then we can say set value, and here it takes the index directly through definitions. Okay, so set value, bend angle, and in this case it's 90. So you can see how it differs from this older mechanism with the iParam array. So now we've got the bend modifier set up, and we can go back to our derived object, okay, which has a relationship with the cylinder already, and the derived object we're going to add the modifier to. So this is what connects the object and the modifier together. The derived object handles that. Okay, so now they're connected, and we need to put it into the scene. So we go to the node, to the interface, and we create an object node. We get the node back. We pass in the derived object. And then we can set the node's name, and then at the end, because we've constructed some relationships, we have to redraw views to get 3ds Max to update the scene accordingly with the new geometry. So this is worth taking a look at. So over here I have the example running. I'm going to say create modifier, and what you can see is that I in fact get a cylinder that's bent 90 degrees, and if we look at the modifier stack, you can see it's a cylinder with the bend modifier, and there's the 90-degree angle. Okay, again, if you have any questions about the exercises, feel free to drop me an email and I'll try and help you through it. Okay, so that brings us back to the presentation for today. We're going to talk about transformations, the scene, the nodes, and the scene graph. So again, more details of transformation. We touched on all of these topics yesterday, but I think it's worth digging into the details so that you have a good, deep understanding of these basic concepts. So first of all, let's talk about transformation and rotation. There's two main transforms that affect an object. The first one is the node transform, that is basically the result of the transform controller plus any inheritance from its children. Okay, so the transform controller we'll talk about in a minute. And then applied to that can be an object offset transform that positions the geometry relative to the pivot point. So this first point, this first item, is essentially the transform to where the pivot point lives. And then the object offset transform is further transformation off of that pivot point. Okay, so remember yesterday when I showed that box and I had that little offset right at the end, and when I did the rotation, it rotated around the pivot point that was offset from the actual geometry. So that's what that's all about. So transformations are represented through matrices, and we have a data type called matrix 3, which provides the translation, scaling, and rotation components. So it's a 4x3 matrix, so it's basically a float matrix that is of dimension 4x3. Okay, it's just an array. Right at the beginning here, I'd like to point out that there's a really good sample, and I'm going to actually run that sample later on today. It's in the Max SDK. It's called Transform Matrix Visualizer. And what it does is it basically shows how the different transformations affect an object. So let's talk about the different types. So at the top here we have translation, and you can see that's a very basic one with just the bottom row of the matrix filled in. Okay. Rotation is a little bit more complex, and you can see where the rotation components live within the matrix itself. All right. And then finally, scale. Scale is something applied across the different rows of the matrix. Okay, and this is how the matrix can be built up to combine the different types of transformation within the single matrix. So matrix 3 can be used as an axis system. So you would basically start by creating an identity matrix, and then you apply the transformations to the matrix to put the matrix into a coordinate system that you need. And here's an example. Basically, if you had an axis system that was rotated 45 degrees around the z-axis and centered at 10, 20, 30, you could use the following code to build it. So you'd start off with an identity matrix. You would rotate around the z, and you see here we're using a little helper function to convert the degrees to radians. So internally, all the angles are typically stored and worked with as radians. So you have to do that conversion back and forth to degrees if that's what you want to show or work, let the user work with. Okay, so we rotate around z that 45 degrees, and then we go and we set the translation component as well. So here's the 10, 20, 30. To further go into rotation concepts, so there's a couple of different ways that rotation can take place. So one of the more common ones is the quaternion representation. So basically there's a 3D unit vector that also has rotation. Okay, and this rotation is limited to basically minus pi to plus pi. So that equates to roughly, or it equates to minus 180 degrees to 180 degrees. And this is represented by what's called the quat class. So there's a quat data type. The next one is called ang axis. Okay, and that's the data type. It is similar to the quaternion, but this one allows any rotation amount in radians directly. And then finally there's Euler angles, and these use the XYZ order for multiple rotations. Okay, and so there's special handling and sign flipping issues. So like for example with the quaternion, you're working from minus to positive 180 degrees, and so the sign can flip, and so there can be some weird things. So there's a section in the docs that I would encourage you to take a look at just for those edge case and the special handling requirements. So the node, first of all, will have a transform. So the local transformation matrix is stored with the node. Then there's an offset transformation that's also stored on the node for the object that's been assigned to the node. Okay, so the node itself essentially contains two transforms. And these can be accessed directly from the inode interface. So node transformation, object transformation, the local transformation, and the object offset. Okay, so the node transform and the local transform are essentially the same. They're just given to you in slightly different relative values, and the same with the object transform versus the object offset. So the idea here is that you transform from the center of the object typically, okay, and that's the default. However, when you apply the offset, then the offsets the geometry. So the transform center is referred to as the pivot point. So this is the node transform. And this is the center for rotation and scaling. It's essentially the location from where rotation would take place and also where the scaling occurs from. So it also defines the transform origin for any linked children. Also defines the joint location for IK, the inverse kinematic system. So the node's local center and the local coordinate system is essentially this pivot point. And it's graphically represented in 3ds Max by the axis tripod. So the red and black axis gizmo that shows you X, Y, and Z is the transform center, also known as the pivot point. So on top of all of this, we have these things called transform controllers, and they have their own coordinate systems as well. So this is the way to provide additional transformation at a specific time. So the job of a transform controller is to update the matrix with its transformation by pre-multiplying its transformation with the matrix past. Alright, so this is where you get the transform animation taking place, because the key here is at a specific time. So these are called PRS controllers. So PRS stands for point, rotation, and scale. They use subcontrollers to create the final transform in this numerical order. So the position controller is used first, and then the rotation is applied, and then the scale is applied. Okay, and these are all independent controllers. We'll talk about controls in another section. So just to go back and summarize all of this, transformation and rotation are contained in two main transforms that affect an object. So the node transform is the result of the transform controller plus inheritance. And then there's the object offset transform that positions the geometry relative to the pivot point. And now we'll switch over and I'm going to show you that sample application. Okay, here we are in 3ds Max. I'm going to go into the utilities list, and there's the transform test. This is a sample plugin that comes in the SDK. It's pointed to in the presentation. So I've copied this over and I've rebuilt it locally, and you can see that it's got quite a few options here. It doesn't show anything until you actually select something, and then you can see all these options light up. So you can do things like get the nodes transform, and here's the entire matrix for the transform. You can get the object transform, and there's all kinds of different things. You can also get the object offset, the transform before a W space modifier, world space modifier, transform after the world space modifier. You can get the parent transform, get the target transform, and you can get the object states transform. So this is the object state is something we'll talk about in the future. So here we can play with different transforms and see how it affects the object. So what we can do here is we can do something like, let's turn all of these off. So the only one we have is use translation. And you'll see my translate matrix, I've put in a 10, 10, 10 for each of the x, y, and z values. If you want to look at the matrix, I've got a breakpoint set here just to show that it's a live demo. And here you can see the matrix set up with that translation of 10, 10, and 10. Okay, so let's go ahead and say update the nodes transform. And there it goes. So it's updated. Now if I go up here and I get the nodes transform, you can see from the node itself that it's translated to 10, 10, 10. Okay? So this is a very useful utility that allows you to kind of debug and understand how the transformations work. So if you have a very complex scene, and you don't understand why something is not transforming or your calculation of the transform is not matching, what you can do is load this utility up and walk through it and look at the parent-child transforms and build it up and test it and see how 3ds Max is actually computing it. So very, very useful utility. Okay, so this brings us to talking about scenes. So first of all, at a very fundamental level, the Max format is a scene file. So the .max file that lives on disk is often referred to as the scene file. It could also be called the model, etc., but typically it is the scene. So this is a 3D model which contains objects, materials, properties, modifiers, and controllers. So pretty much anything that lives within the scene falls into one of these categories. Scenes can also include dependencies. So this might be on another Max file, so using the XREF facility to XREF objects or the entire scene. Or it could be dependencies on other file formats, such as bitmaps or sound files, and maybe even other geometry files. So scene objects are considered parametric. The properties are often exposed as parameters that the user can control. So this is usually through the parameter block system, which we'll talk about more later. Objects that can be assigned to a node in a scene will derive from the object class, and then there's even a lower level class called base object. But for example, geometric objects, which would be the geom object base class, light, which would come off the light object base class, cameras, which would be the camera object base class, and other examples such as particle systems and the world space modifiers. Okay? So don't confuse world space modifiers with a regular modifier, however, because a regular modifier is attached to an object through the I-derived state. But a world space modifier lives in the scene just like any other object. So that brings us to the scene graph. So any information about scene objects as well as their relation to each other are stored in this data structure known as the scene graph. Each of the nodes in this graph is an object of the class I node, and then that corresponds to one scene object. So each I node has information about its corresponding scene object, including a pointer to the object, the number of child nodes, the address of the parent and the child nodes, the position, rotation, and scale transforms, and the material applied to the object. The root of the scene graph is retrieved via the method getRootNode. Okay, this is off the interface class. And then from there, children of each node can be accessed directly by using number of children and then iterating over those by getting the child node at a specific index. Evaluation is, which we mean really is like the update or display of something, is through the eval world state. So this happens by the system, so each of its nodes within a viewport area that needs to be redrawn that happen to be invalid will get an eval world state called on them. Nodes that are not visible in the viewport are not evaluated at all. There's no need to evaluate a node if it's off the viewport. So when displaying the scene graph, the system is basically going to use a technique of minimal culling. So this is based on the 2D viewport rectangle. And this is mainly to maintain the frame per second rate during animation. So to do this, an adaptive degradation rendering system is used. And then finally, the bounding boxes and gizmos and other things that are drawn that are not part of the scene directly are drawn after the nodes. So to iterate the scene graph, there's a preferred way, which is to use this interface class called iScene, and it has an enumeration that helps you to enumerate the tree. Basically, a pointer to the iScene can be retrieved using the method off the interface called getScene. And then you call this method enumTree, which takes a callback object as a parameter, and that callback inherits from the iTree enum proc. And I'm going to show you an example of that in a minute. So, as I showed you a couple of slides ago, you could also use the inode methods, and this is a little bit easier to access, but it may not be as quick or efficient as the enum tree. So you would start with checking if it's the root node. If you have a particular node, you might instead just directly start with the interface get root node, so you know you have it. And then there's functions like get parent node, the number of children, which is what you would start with to iterate the full scene. Get child node, which would be basically an index to the next node in a node's children set. You can get the name of the node, you can get the object reference, so it's basically a pointer to the object that the node is wrapping. And you can get things like the node transformation, which we talked about already. So a term that's not used very often but is kind of an important idea is links. So each connection between a node is called a link. And a link is made from node A to node B if the state of node A, which is its position, rotation, scale, material, etc., depends on that of node B. Okay? So that would be a parent-child relationship. We talked about that earlier, where the parent transform is going to affect the child's ultimate transform. So each object can be followed or linked by many objects, but can link to only one object. Okay, so it's a one-to-many relationship basically. And a loop is not allowed in the links of the nodes, so it's one direction only. So with the idea of the scene graph, you have one root node, and then the links go down from there. So it's one at the top, and you could have, of course, many, many things in the scene with many parent-child relationships. So this scene graph is really just a tree data structure. The root of the tree is a virtual node with no parent. So there really isn't even a visual aspect to the root node. Nodes corresponding to the independent scene objects that do not have a parent object in the scene are first level nodes in the tree. And then objects must have a corresponding node in order to be displayed. So objects that you want to see have to have a node assigned to them. And this leads us to some code, and I think this is going to be where it really becomes clear, is just taking a look at how simple the code can be to iterate the scene. So here we are in 3ds Max, and I've got a cat rig actually loaded here. So I've got a plugin that I've created that's an exporter, and this exporter exports the test file type, and I'm going to select this file to output. And an exporter has some configuration options. So I use the configuration options to allow me to switch between using the scene enumerator or the inode methods. Okay, so I'm going to use the scene enumerator first because the documentation says that's the preferred method. So I've got basically it's set up to start with the scene enumeration. So you see the first thing we do is we get the scene from the interface 7. Now this is one of the versioned interfaces, so you have to do some casting on the interface itself. All right? So I call get scene, and now I have an interface to the scene. So the scene is important because that's where you start the enumeration. So I have a class called scene enum proc, and I'm going to construct a new instance of this, and I'm going to pass the scene in, and I'm also going to use the current time. So the current time can be important because an object that is animated, for example, maybe with a modifier and it morphs over time, when you export an object, it's kind of a static instance of that object, and at that point in time you probably want the geometry. Okay, so that gives you some options there. And then you can optionally do selected only, and that's just part of the exporter. So in this case, I'm just going to go ahead and let's take a look at the scene enum proc. Okay, so you can see it's derived from the iTree enum proc, and I can define anything I want in here, but I must have a callback. All right. So first of all, here you can see this is my constructor, and we passed in the scene, so I'm going to create a reference, a pointer to that scene, just so I can keep track of it. And then what I do is on the scene itself, I call enum tree, and I pass in the class that's derived from iTree enum proc. Okay. And then the implementation of the callback is basically you're receiving the node that the enumerator is currently on, and then you can operate on it. Okay, so once you receive the node, you can do certain things. So in this particular case, I'm going to get the world state of the object, and that's again going back to that time value, and give me the object at that time, and the object's mesh, for example, is going to be a representation of the modification at that point in time. So that's why we do this, just to kind of show how time can affect what you're exporting. But the important thing here is that you do get the node, and from the node you can do things like, well, let me have the superclass ID of the object. And then I can do things like filter things out if I don't want to export certain object types. So maybe I don't want to export helper classes, maybe I don't want to export light classes, and then in this particular case, if it's a light, then I do some further checking. If it's a spotlight, then I just break. Otherwise, I go ahead and output it if it's a gen light. Okay, so just some simple examples here. And the default is just to output it as well. And at the end, if nothing has gone wrong, or perhaps you found what you want, what you can do is you can return different statuses. So there's basically 3 different statuses here. Tree continue is the most common, and that's going to allow the enumerator to continue processing the nodes until all of them are done. You may also want to just ignore the children. So let's say maybe you just want to enumerate across the scene's top level nodes. You don't care about any of the children. So this would be a nice option to use there. Or in the case of, oh, I found the node that matches the criteria, and it just happens to be the first node that was found, and I don't care which node it is. As long as it matches my criteria, I want one of those, I can abort as well. Okay, so let's just go ahead and run this. So that output a file called test, and this is the example here. So I just output some data. So I'm outputting a begin block, and I'm saying it's using the scene enum proc. And then here's all the node names, and I also just happen to output the object type from that scene, and then there's the end. So basically iterated over the entire scene. I'll put all the different nodes, and you can see these are all uniquely named. None of them are duplicates. So it basically grabbed the whole scene. Alright, so that's using the enum tree. So let's go ahead and do an export, and this time let's choose to use the inode methods. Okay, so I'm going to step into my code here, and now I'm true, so I'm going to use the inode technique. So even though the documentation says the enum proc is the preferred way, to be honest, I prefer the inode technique. It's just a little bit more obvious what's going on, and it's a little easier to set up. So it's always up to you, of course, which one to use, but this one is also very useful. So don't just avoid it because the docs say the other one is better. So this is basically using a recursive technique. So you see the first thing we do here is we get the inode of the root from the interface. Okay, so we don't even have to get the scene object in this case. We just say give us the root node, and we make sure we check to see that there is a root node of value, and then we start recursion. So use inode technique, and let's go look at that definition. And you'll see here that it is a recursive routine. So use inode technique. We can't output the root node because it doesn't have a name or an object type, for example. So we just skip it the first time. And then we grab the data. So again, we get the world state of the object. And really what we're getting is the name and the class type, which is the class name. And then on that node, we get the number of children, and then we iterate over the number of children for each node, and this is where the recursion comes in. So for each node, at a specific index, get the child node. We pass that child node into the use inode technique function, and now we're in a recursionary situation. So one of the benefits here that is probably a little bit obvious already is that it's very easy to just know what level you're at in the recursion. So if you're concerned with parent-child relationships and you want to see that somehow or output that somehow, you can do so very easily. Now, there are ways of doing that with the enum tree method as well, but here it's just a little bit more obvious. So I'm going to go ahead and run this again, and here's the same output, but this time using inode methods. And all I did was I put in some indentation to show the parent-child relationship. So these are nodes owned by the scene at this level. Okay, so owned by the root node. And then when we get down here, there's the pelvis bone, and under that there's a child node, that's the pelvis, and under that there's a child node, that's the thigh, the calf, the foot, all the way down to the toe. And this is for the left side. And then we go to the right side, and there's the thigh, calf, foot, and toe. And then we go back up to the pelvis. Oh, and now there's the spine. Okay, so you can see very quickly the hierarchy that is in this particular scene. Alright, so that brings us back to the presentation. Now what we're going to do is talk about inode in depth. Okay, so we talked about inode yesterday and some already today. So some of this is review. But we're going to look at some details of inode that are very important to know. So we're going to dig in a little deeper here. So the functionality includes a pointer to the scene object. So remember that any object that you want displayed has to have a node, and the node kind of wraps that object. So the node has a pointer back to the scene object. It also maintains information about modifiers applied to the object. We talked about the transform and transform controllers that the node handles. Talked about that earlier today. It also stores information about the material and managing the appearance of surface properties through this material. And then it stores node tree hierarchy information, so this is where the parent-child relationship stuff comes in. And then there's also sub-animatables. So let's look at this in more depth. So here's the reference details. At a high level, we have the transform controller, the object reference itself, and then some other things like the pin node for inverse kinematics, the material reference, the visibility controller, the image blur controller, and the layer information. So let's first talk about the transform controller, and again this governs the position, rotation, and scaling typically, so that's the PRS controller for the node in the scene. You can get and set the transform controller used by the node using the inode get TM controller and set TM controller. And I see a typo here, I'm sorry about that, that should be set instead of get. So again, most nodes use this PRS transform controller, for example any geometry like mesh. But there are some other items such as the target spotlights and cameras that have targets. They use a different one that's called the look at transform controller. The next one is the object reference. So again, each node maintains a pointer to an object. It can be a base object such as mesh, light, camera, etc., or a derived object, which is typically a modifier. And this is accessed and assigned using the methods getObjectRef and setObjectRef. And then the material reference, so there's basically a single material assigned per node, and this is a pointer to the material itself. Okay, so you can get and set the material using the methods getMaterial, MTL, and setMaterial. And when assigned, the reference tracks it. So these are not assigned by default null initially. The next few miscellaneous ones here, the pen node for inverse kinematics. This one is using the raw getReference API on the node. So you would say getReference at position 2, and this is always going to be the pointer to the pen node for inverse kinematics. And again, this is going to be null initially. The next one is the image blur controller. This one has methods getImageBlur, mult controller, setImageBlur, mult controller, and these again are not assigned initially. And then finally, the last one is layer, and this one can be directly accessed again using get reference. And this one is at a defined index, so use the definition there in case it changes for whatever reason. And that is node underscore layer ref. So we also have the inode parent-child. So again, there's these parent-child node links. A node may have several children, but only a single parent. Okay, so you can check if a node is linked using the getParent node. If the pointer returned is the iRoot node, then the node is not linked. Otherwise, if it's linked to anything else, it is a linked node. So you can manipulate the hierarchy in this parent-child relationship using these methods. So there's attach child and then detach. All right. And then there's also the APIs that we've already looked at, the number of children. You can do things like get the parent node, is the root node, and get child node. So and then another miscellaneous topic here we should talk about while we're talking about scenes and nodes. Basically, 3ds Max plugins that use assets must declare and identify an asset. You must also persist the asset data, and then you expose the assets to 3ds Max. So there's a whole section in the documentation that describes this, but I wanted to point out that depending on what type of plugin you're working with, assets can be very important, and it's not always obvious that you need to do these things. And then the last thing I'd like to mention is custom scene data. So there's 3 different ways that you can use to create scene data that's appropriate for your application. The first one is using custom attributes. So this is the recommended method, which is to attach a custom data with the scene object nodes. And then the next one is called custom user properties, and this is pretty limited, basically allowing you to associate simple string data in the INI file. Okay, so it's ASCII format, and it's basically some key equals some value. So it's not particularly powerful, but it could be interesting for you. And then the last one is application data, and this is custom data that's accessible programmatically and can allow custom binary data called data chunks to be associated with objects derived from an animatable class. Okay, so this is something that would give you more flexibility, gives you, fast performance because it's binary, but it would be used if the custom attributes themselves do not work. Alright, so that wraps up the presentation for today, and I'd like to go over the exercise with you now. And just to let you know that tomorrow we're going to be talking about the reference system. We're going to spend pretty much the whole lecture working with and looking at how the reference system works. Basically, a reference indicates the dependency between 2 plugins or between a 3ds Max object and a plugin. So the reference system is used for several purposes, which includes notifying dependent scene objects, managing automatic deletion of objects, and loading and saving the scene graph. So the references goes back to this links idea and how the parent-child relationship works. So most references can be observed in 3ds Max using the schematic view. So if you want to become a little bit more familiar with that before the lecture tomorrow, you can go into the UI and look at the schematic view. All right, so let's take a look at the exercise for tomorrow now. Okay, so exercise 3 is basically to implement scene traversal, or basically iterating over the scene. So a common reason to iterate over the scene is when writing something like an exporter. So we're going to use the wizard to create a new plugin that is an exporter type. So the first thing you'll do is you'll go through and you'll just implement all the to-do functions. Okay, there's pragmas in there basically, and just implement the basic things that you need to get those to-dos out of there. And then the entry point for an exporter where most of the work is done, you're going to go into the do export function and create the traversal code. So first use the iscene enum tree. Okay, the docs say that that is the preferred method, and it is a little bit trickier to implement, so I think that is a good one to start with. Get that one out of the way, figure out how it works, and then go on to this next item, which is to use the inode methods. So then you can see the difference between enum tree and the inode parent-child methods. And in both cases, you're going to need to create some sort of output format to put the data into. So write it out to an ASCII text file so you can see the data. And you should minimally output the name of the node. And then optionally, while you're working with the node, if you want, you can output other data associated with the node. So maybe you could output its transform, its offset, its wire color, some of the other interesting things. And maybe even go and get the object that's referenced by the node and put out some data about the object, because ultimately in an export format that's what you're going to want anyways. So that will be the exercise for tomorrow, and I'll go over and cover all of these things again just to review them at the beginning of the class tomorrow. So thanks again for attending day 3, and I'll see you tomorrow at the same time. Thanks.